Alrighty, folks, good morning. May as well get started here. Today, we're starting, it's not really a chapter, it's a handful of content comes from a variety of places in your book. I consider it all introductory material, okay, or, you know, we wouldn't be talking about it now, but, so some of it is in the introduction of the first chapter, and some of it is scattered here and there. So again, for you chapter readers out there, yet if you haven't read chapter 1, please by this point do. But like I said, we will be getting you whole unique chapters, topics per chapters very soon. Very soon. So, what have you been staring at here? A picture of what? The Earth. The Earth? Good. Good, good. What color is it for the most part? Blue. Blue. All right. 75% ocean. Yeah, good job. Good job. It is dang near 3/4 covered by oceans. Not quite evenly. We were looking at the other side, we'd see a lot less blue. Got a big old hunk of continent in the middle of everything there. A couple continents actually, I suppose. What's the green and brown stuff? Land, continents, forested. I think I heard that too. Good. How about the white stuff? Clouds. Clouds. Good. Good, good, good. So, you may have had in your science classes before, science class, whatever, all those O-spheres, hydrosphere, lithosphere, biosphere, this O-sphere, that O-sphere. I don't use those words very much because in the way I look at things, there's an awful lot of overlapping going on. When we get to the layers of the Earth, yeah, we're going to use a couple. But really just, we try to stay away from those words as much as possible. So we've got the surface of the Earth, okay? And on the surface of the Earth, you see, as you guys just told me, you see a whole lot of water, and then you see some land. That land, as we know, is just broken up into continents. And then around the Earth, above the Earth if you want, there's one O-sphere we have to use. We have the atmosphere, okay? And in the atmosphere, we've got our clouds, we've got weather, we've got all that jazz going on. We didn't have this view for a very, very, very long time. It wasn't, of course, until we were able to put stuff up into space that we got to get a picture like this. And even then it wasn't so swell. But nowadays, you know, all over the place. But we've had globes for like ever, right? Almost. So we had an idea of what it ought to look like. But we were pretty dang sure it looked like. And for the most part, they were right on. Okay, so you all recognize the Earth. That's a great start. And some of its important components. Let's go a little further out. A little further out, we got space. Well, what is space? I don't know. You guys want to try? What is space? Yeah.
Vacuum.
Okay, space is a vacuum. That's true. But what is space? Yeah, you're right. You know, don't necessarily have a definition of it. It's another place. It's a lack of stuff, but there's stuff in it. It's kind of tricky, right? Where does it start? Well, there's another good question. we're going to give you some sort of answers on that one. There's no dashed line up there. Space starts here. You know, you don't even have those when you cross states half the time. You might have a little sign or something, but. So hopefully by the time we're done, you have a better understanding of what space is. Not necessarily the stuff in space. We touch a little bit on that, but that's reserved for some other classes. Around us, and for lack of a better word right now, in space, we've got a couple really important things that help us exist. We would not be, well, things would not be the same were it not for the magnetosphere and the Van Allen radiation belts. All right, two horribly important things. They too have a lot of overlap in what they do. So when you're reading about them in the textbook, you might see some slightly different stuff. I tried to, give you unique, specific things that each one is sort of known for lack of a better word. So in here, we're going to say that the magnetosphere protects us from solar winds. And Van Allen radiation belts are responsible for trapping cosmic radiation. Now, again, you'll see in a moment that they're really, the Van Allen radiation belts are kind of stuck in the middle of the whole magnetosphere thing, and it's not quite that simple. But if we were, nudge, nudge, wink, wink, to get, some multiple choice questions about this stuff, that's probably what you would want to remember. The neat thing about the magnetosphere is that the Earth creates it itself. I don't know why. I can't stop. I grew up, Star Wars came out, I was a little guy. And it was, like one of the first movies I remember, really cool movies in any of it. I remember I saw a bunch of Disney stuff with my folks, and they were all right. But the first really cool movie. And I always think of that scene where Obi-Wan is going along that weird little walkway and trying to shut off the force field, the tractor beam kind of thing. I think he was trying to shut off the tractor beam, right? So, what I think about it with this is that exact thing. The core of the Earth emanates, radiates, for lack of a better word, creates this energy field. It's because the Earth is spinning. It's because the inner core, there's two parts to the core, you probably know that, is a solid ball of metal. The outside of there is some molten metal. And the spinning around of it creates an energy field, kind of like a battery. You've got a positive and a negative. You know it as the North Pole and the South Pole, right? But they actually have a charge as well. That's the polarized bit. And Hollywood loves to play with this idea because, it is really important. And when they figure out how, it's just created by the rotation of the Earth, and they try and get Hollywood with it and mess with it. There was a moderately, well, I won't say scientific, but there was a kernel of something in The Core, which was a movie. I think we had, was the other one, Armageddon, where they had to travel to the core with a nuclear bomb. There's a handful. This is a cool image. I always like this image. It looks like a giant blue space spider. Squid, I guess. Too many legs for a spider. But giant blue space squid coming to crash into the sun, right? First thing you got to get is where it's pinched together there. That's your north and your south pole. All right, so let me try and move the mouse so the folks at home can see as well. So right there and right there. So why is it shaped so strangely? Why does it look like this giant spider and not just a ball of energy around us? Yeah. Okay. Comes in waves. It probably does. It probably does. Yeah.
The sun's energy that is going towards the Earth is pushing our energy the opposite way.
Yeah, that's a little closer to what I was fishing for there. I'm sure it's pulses. I'm sure it's not constant. I agree with you. But this drawn out shape, this was probably somebody's grad school project. I don't know if it was a full on doctorate or not. University of Texas, Dallas is where I grabbed the image from years ago. But this is just that, all that stuff that we're telling you that it's responsible for blocking from us, it's all sort of swooshing around us like some big aerodynamics experiment you see, like a car in a wind tunnel kind of thing. All right, it's that reason. So this person thought that the sun's energy would give it that, we got a little solar flare thing going on there, some sort of eruption. And during, when it's not solar flaring, perhaps, it might have a more uniform shape. But we are constantly being battered by cosmic debris, that's for sure. This is a really cool picture, and I apologize, I tried to squeeze text over top of it. I should have just let it be two separate slides, but I wanted you to be able to stare at it while we were talking about it. So the Van Allen belts are an area within the magnetosphere. I bounce back and forth between Neto and Nito. Feel free to pronounce it how you want. It is really Nito. So, that stuff that we were just talking about that shapes the magnetosphere, it gets trapped in there as well. They've only known about this for, it says 58. We found it. This is the reason that it's really dangerous to be in space. This is what we gotta block, you from. Sure, there's random sun eruptions. We've all seen, some series on TV, and you gotta hide from solar storms and so on and so forth. But just the general background crap that makes it dangerous on a daily level, all right, is here. Okay, it's in the Van Allen belts. You might think, well, okay, why don't we just get the hell out of the Van Allen belts? They're big. It's a long way out, and we'd have to go a lot farther out than we want to, and so on and so forth. And again, it's better there than down here, right? There's an awful lot of stuff that the astronauts need to worry about. This is just one of them. You've got muscle loss, you've got bone loss, okay, all kinds of things going on for them. This is just one more. So the Van Allen belts, horribly important. If that stuff didn't get trapped, evolutionarily speaking, things would have been horribly different if they did even get a start. All right. We won't probably talk about it in here. We needed, my opinion, a handful of other people's opinion. We needed a little bit of mutation in the beginning to get things rolling. Right? You want to get a whole bunch of different cells. Well, mutate the heck out of them with all kinds of different radiations. But at some point, you want to kind of filter that out and let things be and see what happens. So this stuff obviously built over time. It says there's 2 belts, sometimes more. So again, the sun's energy varies. Sometimes it's more active than others. You've probably heard that. So this is a sort of I don't want to say a living, breathing thing, but it is an actively existing, changing thing. But there's always something there. And like I said, it is our force field. It is our protector. This slide's kind of redundant at this point, but just shows the 2 main belts. I had this this was what I had at first. I just found that other one, which is a lot cooler.
All right, so let's get a little closer down to Earth now and talk about that atmosphere that we know and love. I let it slip the other day that the atmosphere isn't primarily oxygen. Some of you knew that. Some of you probably never pondered it. You know oxygen is important. But I'll tell you, I was quite surprised when I found out it was only, 21%. It's that important and it's only 21%. That's going to be a recurring theme in here. One of the ones you'll see in a couple minutes is carbon dioxide. Everyone is flipping out about carbon dioxide, right? Or CO2 is horrible. It's melting all the glaciers. It's doing this. It's doing that. And you're going to see that it's a decimal. You're going to say, oh, it's a decimal. That's so tiny. Who cares? What's the point? Sure, we could go up. It's not even a whole percentage. Well, the point is that Mother Nature, I kind of talk about Mother Nature a lot, anthropomorphically, if you would. That's what it's set at. And at 21%, at point whatever for CO2, this is the weather you get. All right? Doesn't matter if it's teeny or it's huge, what we have is a function of what we have. So when you change that, you can't help but change the other. So it's really easy to see, again, only 21%. That's oxygen might not be that important. Now, you've been raised exactly the opposite, so you know this one going in. But when you see some of the other numbers, it's tempting. So 78% nitrogen. You're nitrogen breathers, right? Never really would have thought that. I talked to some of my biology friends years back. It more or less just passes through you inertly. Okay, there's a couple times. Anybody dive? Divers, that's bends. You've heard of the bends, right? That's a nitrogen issue. But otherwise, it's just there. And that's okay. Told you it's the reason the sky is blue. That's important. We have an atmosphere because of the Earth's gravity. All right, that's another big question. Why do we have an atmosphere? Well, we mentioned gravity once or twice, and we told you that gravity is a function of mass, right? And mass is the sum of your matter, and then so on and so forth. So anything that has mass is attracted to gravity. The thing with gravity, again, is that the less mass you have, the weaker the force. So we've got this atmosphere, but it's really close to the Earth. All right? And as, again, you probably know, but never pondered perhaps, as you go up higher, what does it do? Yeah, it thins out and pretty dang quick, right? So that's why. There's less, it's farther away, it's less affected by the Earth's gravity. It's sort of a fade, okay? So like the colors I was playing with before class here, I ended up with not really an effective fade. I went for more artsy than helpful. But, just imagine we started at a dark blue and faded to a really, really light blue. That's exactly what the atmosphere is doing. Really, really thick and dense down here. Higher you go, the more it fades out. We're going to learn about the layers, okay? But one of the ones you've heard about already is the ozone layer. Why do we like the ozone layer? What does it do for us? Huh? Protects us from what? I saw a hand over here.
Sun's radiation.
Sun's radiation. Someone want to tell us which part of the sun's radiation? Yeah. UV rays. And someone else, what does UV stand for? Ultraviolet. Yeah, and we're going to push the limit. What are the two ultraviolets? You didn't want to go for that question. Sorry. He had his hand up a minute ago. UV what and what? You see it maybe in sunscreen and on shirts anymore. That's really all you would have seen it. There's UVA and UVB. I don't know what the hell they are either. But they're there. All right. So the ozone layer helps us, again, just like the Van Allen belts. All right, but this one's in charge of ultraviolet radiation. Filters it out. We had the one, I don't want to say the only time the world came together and fixed the problem, but dang near. We had an ozone problem in the 80s. All right? And it was all those hair metal bands and the fluff chicks that I went to school with the hairspray going shh, and the little old ladies with their 1.5 tall cans of White Rain hairspray. All right? And a handful of other things. But propellants, coolants, all right? Chlorofluorocarbons. That was like the first longest word I ever had to learn how to spell. Were breaking down the ozone. They were in these things for some reason, chemically important to propellants. And that's why all hairspray went to the pumps for the longest time. I think it's back to, you could kind of like press and hold now, it just goes shh for the longest time. But I think maybe they used like nitrous oxide or something, like it's in a whipped cream can or something. But they took them a while to figure it out, so you had to pump hairspray for like a decade. It was horrible. Or so I'm told. I never use that stuff. But at any rate, it made a hole. And the UV was coming through, and it was burning all the baby seals. And no. But it was up north, all right, and folks were worried. So we did what we could. We banned what we could. They removed it. A lot of countries couldn't afford to do that, so there was still some, but we cut it down globally, cut down the levels out there. And guess what? The dang thing repaired itself. We're going to talk a little bit later about the process that makes ozone. All right? And, yeah, it fixed itself because we stopped monkeying with it. So that's sort of the hypothesis they're running with the climate change thing. Okay, we've seen that the Earth can react kind of quickly when we stop poking it. So they're trying. Stratosphere's up there because that's where the ozone is. All right. Stratosphere is one of the ones you'll want to remember. Again, we're going to give you the whole list, but stratosphere is just above the level you guys live in, which is this last word here, troposphere. So we're in the troposphere right now. At some point, it blends out into the stratosphere, and that stratosphere is where we like to keep our ozone. Every so often, we get ozone at the surface. We call it smog at that point. You'd think the way they go on about it, we'd want extra UV protection, but smog tastes nasty. If you've ever been to a big city in the summer, you sort of get that taste in the back of your mouth. That's what it is. So we like it in the stratosphere. We don't like it in the troposphere, even though it's extra protection. All right. Little bit of, I don't know what you'd want to call it. A little bit of formulas, we'll just say. You don't have to memorize these formulas. Please don't worry. You've seen them before. But they're here to try to show you the connection. Give you an understanding of what's happening. And it goes back to these little tiny particles that you can't even see, but you can feel it. You move your hand back and forth, you kind of feel that little bit of breeze. All right. You know the particles are there. So I want to talk about pressure and density. Formula for density is mass per volume. You probably knew that one. D equals M over V, right? At least you remember being tortured by it. Pressure, you might not remember. Some of you do more than others. Pressure is force per area. And instead of over, I'm saying per. And just like the homework problem in the lab book, all right, this little sign here is also a divider. All right, you would say mass divided by volume, force divided by area, but I'm saying per. It's all the same thing. We, for the last 3 years, have had we were one of those families that got a COVID dog. All right? Everyone's sad with COVID, and there was a huge boom in dog purchases. Well, we ended up with a 65-pound poodle. Yeah. So when that poodle,
stands on my lap, especially just one leg, right? That paw, all right, the force per area, I got 65 pounds pushing down in what, 3 square inches, 4 square inches. It's a lot of force. You can feel it. I don't know anything about her density, but all right, so what does that have to do with what we're talking about? So remember how we told you the atmosphere thins out because of gravity, right? It's thicker close to the Earth because of gravity. It thins out because, well, there's less gravitational attraction out there, and because they're so light. Well, you should say less dense, right? But we're going to say light. You know what I mean. So we're going to tell you that both air pressure and air density decrease as you go up. And the why, and we already told that should have been, let's say that should have been obvious when we told you that it was thicker near the surface and thinner up there. But for those of you that weren't on the bus yet, let's explain that. So density is simply put mass per volume. All right. You've got more air molecules close to the surface than you do 5,000 feet up. If you just drew some random circle to equal your volume, indicate your volume, there would be more air molecules in it at the surface of the Earth than there would be way up high. You knew that already. All right, that's all this air density thing is telling you. Except we're not counting particles, we're talking about their mass. And the volume is arbitrary. You look outside and you don't see, things. And that's why usually when I talk about this in the olden days when we draw on the board, I would always draw just a little fluffy cloud. All right? Because that gives you some boundaries. That's something you're familiar with. It's measurable. The pressure is essentially the same idea. I did put it in there. It's right at the end. As I said, I did not tell you the equation for force, because we just jumped straight to pressure is force over area. But guess what force is related to? The last equation there, mass. So what we're looking at, and again, I'm going to use this word sort of incorrectly. When we're talking about air pressure, we're simply measuring the weight, incorrectly used, the weight of the molecules above you. Usually they'll tell you 1 square inch, a column 1 square inch kind of thing. Okay? So it goes to figure that if you're at sea level, are you going to have more or less air molecules above you than if you're at the top of a really tall mountain? Where are you going to have more molecules above you? Top of a mountain or at sea level? Sea level. So where's air pressure higher? Sea level, because you got more stuff over you. Again, if you automatically start freaking out when you see equations, you're going to go, this doesn't make sense, this doesn't make sense. But it does make sense. You guys just all nodded your heads. It makes perfect sense. So I'm not going to show you those equations ever again. Like I said, I just wanted you to see that it is, math is helpful for once. That it is all sort of connected, and it goes back to, the mass of the molecules and gravity's effect on them. So again, boil it all down into a multiple choice question. Both air pressure and air density blank as you leave the surface. They decrease. All right, if it were short answer essay questions, which we used to have some of, well, then you'd have to explain a little bit more. But I'm letting you off the hook, I guess, by doing that. But I think that you get it. So anyone want that explained again or differently or anything like that? Okay. Well, here it is again anyhow. This time in a convenient graphic in metric. This is kind of neat because it shows you Mount Everest, and everybody knows how big Mount Everest is. No, we don't, but we know it's really huge, right? So one of the things you could take away from here is that by the time, well, let me rephrase that. Before you get to the top of Mount Everest, you've got half of the atmosphere below you. You know, like by percent mass kind of thing. I'd say you're about 3/4 up the mountain where they drew their line. So that's a really tall mountain, we knew that. But maybe you're surprised at how quickly the fade out is. And you see up there where airplanes fly. You know that airplanes have to pressurize their cabins, create that artificial pressure. So now you know why the air pressure is lower up there. There's less stuff. Now, why that actually matters is because you are a pressurized system. Okay? Doesn't really come into effect for most people. But if you think about it, you are a pressurized system. You've got an internal pressure. Yeah, you got a skeleton holding you together and all that, and keeping your shape and form. But you have an internal pressure that more or less equals the external pressure. Okay, it doesn't affect the average person, but if we take you to the bottom of the sea, you get crushed. Why? Well, because the pressure down there is immense. And what have we all learned from watching old sci-fi movies? If you go out into space without your helmet on, you expand, right? They blow up. I'm not entirely sure that's true. But the idea is that you're a pressurized system and you are way out of your equilibrium there. But actually most folks are familiar with this because anytime you go up and down hills in the car, what do your ears do? Many of you. No, nobody's only me. Yeah, they pop. Yeah, your ears pop if you're going up and down a really big hill. Maybe it's just us folks with sinus problems. I don't know. But, bless you. But, huh? Okay. Yeah, for some folks, like I said, and I'm one of them, all you need to do is come down a really big hill sometimes. And then maybe it's a speed thing if you come down really quick versus whatever, but your body can notice it. But yeah, definitely in airplanes. So the text on here just sort of reiterates what we talked about in the previous slide. This was more for the graphic. All right, so what is air pressure? Well, we told you what air pressure is by definition. By constant or by numeric number, it's 14.7 pounds per square inch. Now, 14.7 pounds isn't exactly heavy, but if you lift up something that's 14 pounds, all right, you notice it. It's a couple-month-old baby, so to speak. You pick that up, it's not, a loaf of bread. So why don't you notice the fact that you always have 14.7 pounds of pressure pushing down on you? You're used to it. You've been under 14.7 pounds of pressure since the moment you were born, and your pencil is under 14.7 pounds. Your water bottles, your headphones, everything you own. So it's just that's your equilibrium. That's your flat line. I can't think of the word I want to use. That's your normal. Now, of course, the meteorologist couldn't be happy with 14.7 pounds per square inch. That's you could measure that, I suppose, that way. But instead, they came up with this really funky device called a hygrometer. All right, and this is the number you actually see when you're watching the news, or more so nowadays, you're looking at your app. If you actually have air pressure listed on your app as one of your features, I really dig air pressure. I was so thrilled when the iPhone's got barometer, so I was super excited. I got the barometer at. But 29.92 inches of mercury. It's kind of like a U-shaped tube, okay, filled with mercury, which we don't really like to play with anymore. And the air, so one side of it is calibrated, kind of has like the little lines on it for a ruler. Calibrated means. I see a lot of you frantically scribbling down what's on the board here. These are finally up, by the way. These are on your site. Okay. So you don't have to write everything down. Ideally, you bring them with you, print it out, and you just take notes. Anywho, so one side of it is calibrated in inches, and standard atmospheric pressure. You take one of these to the ocean with you over the summer, and it pushes the air pressure pushes that mercury up to the 29.92 mark. If the air pressure increases, we get a whole lot of, say, humidity in the air. All right, that should go up a little bit. If it's really, really dry, you somehow find a desert at sea level, and you go to there, and you might get it down a little bit. It doesn't really go that much one way or the other. Okay, but it can move a little bit. I want to say I've seen 30, but I don't remember how low I've seen. Yes, sir. That is mercury. The elemental symbol for it, mercury. Great question. And ATM, by the way, is 1 atmosphere. Since I'm pointing out what I should have said earlier. That's a standard atmospheric pressure. That's what we call 1 atmosphere. Okay. And IN is inches. The way I like to think of this is, remember that you used to see them only at like Spencer's and stuff, but now you can find them anywhere. They've gotten so cheap. Those little rectangles filled with, I'm going to call them pins. They're not super sharp, but they take the impression of your hand. Usually you see them sitting on the shelf with the middle finger sticking on and so on and so forth. Yeah. If you could imagine walking through that as it goes up, and you would push it up and down. That's sort of how you're walking through these columns of air. Okay. Again, you don't see it. You don't really feel it unless it's moving quickly. But that's the idea. And as one of those pins is up, that's a shorter column of air above you, and it's kind of a neat visual. But like I said, I don't even know, do we still have a Spencer's in our mall? Yeah. Mm-hmm. That is our mall. Okay. Unlike pressure and density, temperature varies wildly. Temperature is that red line. And a move to the left is a decrease. A move to the right is an increase. So you guys can tell me that during the trip upwards through the troposphere, which is the first atmospheric level, the white one down there on the bottom, what does air temperature do? I didn't hear you. Decrease. It goes down. And again, you knew that walking in the door, right? We all knew that. Those stories about people trying to smuggle themselves in the cargo bays and this, that, and the other things of planes, they freeze. There's another much more practical version of it. You still see the hats have made a comeback, but the jackets not so much anymore. When I was growing up, we all had what we called the bomber jackets, and they were either the leather ones or some other material, and they had the big like faux sheep shearling thing on it, and then the hats, right? The hats are still around. But why do we call them that? Well, because the guys that used to fly those airplanes in World War II, they had to wear those things. Why? Because it was cold as hell up there. Oh my God, they were so cold. That's why they wore them, not because they looked cool. They were freezing. All right, but over the years, you know, things make their way into fashion and so on and so forth. So we know this. The temperature decreases as you go up in the troposphere. Well, what you probably didn't know is the rest of it. All right. So we want to focus on the rest of it. Once you hit the stratosphere, you see that it's the names are sort of off to the right side of the colors. Don't worry about the pauses either. You're just going to learn the O-spheres. So the stratosphere is next. We told you that's where the ozone is. It's important there. Stratospheres where your airplane can go. No, airplanes don't go that high. No, they do. Yeah, they do. I lied. Your airplanes are up there. 30,000 feet? I was just in a dang airplane. 5,000 feet to a mile. Yeah, it's close. It's close. Red Bull guy jumped out of into the stratosphere. I don't know how long I've been telling that story. He needed a special suit. And it was a pretty crazy jump, but we have done, we'll call that a free fall from the stratosphere. But otherwise, we try not to mess around up there too much. You need special equipment to go that far. And that's what threw me off when I finally did find the altitude in miles there on the right-hand side. Six miles. 7. You got 0 and 10, and that line in the middle is 5, obviously. So you're at, what, 6.5 miles, you enter the stratosphere. That's always kind of blown my mind, how freely we can jet about the surface of the Earth. All right. Some of you may have taken a road trip or two this summer. So you went up into the atmosphere then, but for the moment, let's stay on the ground. And all your really limiting factor is time and gas money, right? You don't need anything super special to get from here to Buffalo or here to LA, even if you wanted to. Again, just time and money. Well, let's keep it simple. I forget what I was looking at yesterday, but I think I was ordering some food for lunch or something, and Google so helpfully tells you all this information. It was 5 miles to Commercial Drive. So you can't go from here to Commercial Drive vertically without needing special equipment. That's kind of crazy. You certainly can't go down. Down's a little easier to picture because, well, obviously there's solid Earth. We got to, But you think about it, if you're watching Discovery Channel, you see these guys coming up from the mines. They're practically just in nothing but a loincloth, and they weigh 73 pounds. And, it's crazy down there. All right. And going up, like I said, if you could find a road, so to speak, that took you up there, you'd be going through some serious issues with your body. So things change very quickly vertically around here, but horizontally, we're pretty good. We're pretty good. Anywho, lest I digress. So the temperature kind of evens out. It drops down to where is metric, or where's the good old American here? It's on the bottom. Looks like we dropped down to about 60 below zero by the time we hit the stratosphere. It levels out there. And then by the time you hit the next level, the mesosphere, you're almost back up to surface temperature, average surface temperature, which is right around 60 degrees Fahrenheit, by the way. Looks like it's just a little below that. I'd throw her in 45 to 50 maybe. Then it goes down again, and I'm not going to quiz you on those numbers. Don't worry about that. I'm just talking. Goes down again, and then it starts to go up. And the chart ends. Well, it's called the thermosphere. Now, some of you know that therms are a measure of units and so on and so forth, but generally speaking, when we use the word therm, what other word comes to mind? What are you supposed to think? Thermostat, heat, I think I heard it back there. Heat? Okay, hot. Therms usually imply hot. A thermos is going to keep stuff warm. It could keep stuff cold too, but usually we use a thermos to keep stuff warm. Thermostat, we want to make us warm. Therms tend to make people think of warm, and that's what they're going for here. All right. There is a level beyond here you're going to see on a subsequent slide. Exosphere. All right. But this ends at thermosphere. So the idea is that this is hot. like, well, wait a minute. All right, we're going here. The chart ends. We're barely at 0 when the chart ends. But the implication is it keeps going up. But you've always heard the cold, hard vacuum of space, right? Space is cold. If we don't have astronauts' heads blowing up, we certainly see them freezing. That's sort of been the thing lately. You guys watch For All Mankind? It's a pretty good series. But you got to have the Apple box, I think, to watch that one. That might be an Apple production. But they had a lot of people freezing out in space and so on and so forth. Yet this diagram here is telling us that space is going to be hot. Well, how does that work? Or is one of them lying? Or can they both be true? What do you guys think? Both? Well, how could it be both, young man? Sounded like a good answer. All of the above? By the way, when I give you all of the above, it's typically going to be, I write like question sets, and every so often I tend to use all my answers, except for the really silly one. But if I give you all of above, it's going to get used probably in one of those questions. All right, so what do you guys actually know about temperature? What is temperature a measure of? A measure of energy. Somebody else? He's right, but that's not exactly what I'm looking for yet. Yeah. That's what we're looking for. All right. It's a measure of molecular speed. Not everybody knows that. I must have been doodling when my teacher said that, because I didn't know that for years. Absolute zero made no sense to me. I just thought it was so damn cold that even molecules couldn't move. Okay? Because that's what absolute zero is, right? It's the ceasing of molecular movement. You're like, oh my God, they froze solid? They froze a hydrogen atom? How, No. Temperature is a measure of molecular speed. So, as you slow down a molecule, it gets colder, so to speak. As you speed it up, it gets higher. And it is a function of energy, so that there's the connection there, right? Okay, so let's keep the application going there. So we're in space, and we know that it's supposed to be hot, but apparently it's really cold. How does that work out? Well, let's think about some of these past slides that we just saw. What did we tell you about air molecules up there? Yeah, they thin out pretty dang quick. Now, we used the word vacuum a little while ago. It's not, I would say it's not 100% true. There is stuff up there. It's just really, really, really spread out. Temperature is a sensation. It is molecular speed, but from our perspective, it's a sensation. You have to experience it. You have to feel it. All right? So if you're in that void that we talked about, you're going to feel what? Nothing. But if one of those little suckers zings by, you're going to feel really, 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 really hot. Because it itself is moving so quickly, the molecule is moving really hot. So that's where this whole exosphere and thermosphere come into play, where the temperature does increase, okay? Because there's so little stuff out there, there's very little friction, if any, okay? It is negligible, can't be zero, I'm sure. So things are going to move as fast as they can possibly move, so on and so forth. So if you did, and when you did come in contact with some molecules randomly here or there, it's going to be really, really fast moving, hence really, really high temperature. But for the most part, you're going to be void of feeling that stuff. All right, let's do one more thing with the temperature, and then we'll move on. Because I know I lost a couple of you on temperature as a sensation. I want everyone and you folks at home find something
to do this with. I want you guys to touch one of the metal parts of your desk. All right, with your same hand, I want you to touch your notebook. With the same hand. Let go, and then touch the notebook. Well, no, you can let go. Let go of the desk. There you go. All right, do it again because we had too much of a pause there. All right, which one's colder?
Metal.
The metal. Why would the metal be colder? Touch your neighbor. No, don't touch your neighbor. But everything's the same temperature, right? Your desk does not have an internal source of heat, nor does your notebook, right? You do. You have a temperature. But your notebook doesn't. The desk doesn't. What did we tell you about temperature? It has to be, you have to feel it, right? Somebody said the word. What is metal a good water? Conductor. What's actually happening? The metal isn't cold. Your finger's cold. The metal is better at pulling the heat out of your finger than the notebook is. It's stealing your heat better, more efficiently, quicker, whatever you want to say. So it feels colder than your notebook does. They're both the same temperature, though. Just thought you might want to know that. All right. See, isn't that more exciting than vocabulary words? We don't know the vocabulary word. You actually just learned something. Lapse rate. So this goes back to the troposphere. Lapse rate only applies to the troposphere. We've got words for it, whether you're in water or if you're in air. There's a handful of words that talk about temperature change in this chapter. Okay, so try to keep them straight. There's 2 of them, but I throw a third real one in the multiple choice answers that some of you might have heard of. So lapse rate is the decrease in temperature with an increase in altitude. So in other words, as you go up, feel free to substitute your own words in here. These definitions seem a bit wordy. And it boils down to about 3.5 degrees Fahrenheit per 1,000 feet. So if you go up a mile, or 5,280 feet, 3 times 5 is 15, and half of the 3 and 1.5, you're about 25 degrees cooler, 24 degrees cooler. What is 3.6 times 5? 18. Well, I was way off. I was giving that half some more credit than it needed. Just about 18 degrees cooler a mile up. And I use 5,000, but I'm still not going to get up to 24. So again, why when you go up? Okay, it's actually measurable. You know what the temperature should be at any given elevation should you need to know that kind of stuff. Again, the average person doesn't affect you. If your car's up that high, you're in trouble. Okay, you don't need to worry about the temperature. But this goes back to that red line. Now, whether or not this is truly accurate from there to there, but there is an equation for it. Oh, for you folks at home, sorry, I pointed on the board, talking about from here to here. That's the lapse rate. Alrighty. We've used these words. Now you're just seeing them. So the troposphere goes up to about 7 miles. Another thing, and I'll say it before you guys write it down, and maybe someone brave enough to ask, that little squiggly there, the tilde, that means approximately. Okay? About. It's a big thing about geologists. We like to say about a lot because we deal with such huge units of time and stuff like that. Who can really be exact? It's for engineers. Many stories about them arguing on job sites. So about 7 miles.
Yes, your book will tell you the exact number, and if you want to memorize that, God bless you. Stratosphere goes from 7 to 30 miles, mesosphere 30 to 55 miles, thermosphere 55 to 300, and the exosphere, which again we're calling space, 300 to oblivion, wherever. So space is about 300 miles away. I put 1,200 miles on my car 2 weekends ago. Could have went to space a couple times, apparently, had I the proper equipment. So it's a lot closer than you think. It's tough to get up there. All right, and we won't, spend a whole lot of time. We do some little more talk about space in the next lecture, but it's really hard to get to that 300 miles. I mean, you've seen rocket ships, right? 95% of that thing is usually fuel. Gravity, friction, atmosphere. That's the whole point of the space station in the long run, right? Bless you. Is just that, a space station. We're going to try to figure out a short way to get to there, and then we use that to get somewhere else. Because it's super expensive. But it's only 300 miles away. All right. So we touched on this earlier. We're kind of just bringing it all home now. We've been focusing on the atmosphere for the most part. And just want to wrap it up with nitrogen is 78%, oxygen 21%, and that does not add up to 100, right? So there's other stuff out there. Water vapor, 0 to 3%. I know some of those nights we just had not too long ago, some of those days, it felt like it ought to have been like 25%, right? But again, it is what it is. And when you put that small amount of water vapor into the air, you actually feel it. Argon, no idea what argon's doing in there. But it's there. We got some. CO2, I mentioned this one earlier. 0.035. And that's what people are like, that's a little. But that amount gives you what you see out the window. So it's just right. It's just like, when you're baking your grandma's favorite cookies or something, special cookies, and she has a secret, you just put a pinch of this in. It's that pinch that just makes it just right. All right, that's where it is. Other. Well, there's a lot of stuff in the other. Everybody's favorite, nitrous oxide's in there. So if you're feeling a little happier one morning when you wake up, maybe the nitrous levels are just a little higher where you live. You never know. Dentist office next door has a leak. It's laughing gas, for those of you who don't know. But again, the biggest thing is we're primarily nitrogen and oxygen, okay? Because in this mix, we have to put in all those pollutants that we worry about, all right? All of the, we're not really going to measure the particulates, but some of the gases, there's gases in there. And like I said, just a whole variety of things, all of that water vapor, because we can't really go over 100%. So we don't have a whole lot of room to mess with the 78 and 21. And again, I rounded. I yell at you guys in lab. Monday lab you didn't get yelled at yet. But about all your rounding, these are rounded. Do you want to memorize decimal percentages for the test? No. So we did round a little bit. But okay. So this is a good pausing point. This is typically where I pause. We're We're going to move on to a different conversation when we come back on Tuesday.
All right. I'm going to pause the recording.